Thank you. So thank you very much, everyone, for being here. So for this reading group, I'm going to present an article called Coverage and Capacity of Joint Communication and Sensing in Wireless Networks. So this article is from 2022 and from Nicholas Olson, Jeffrey Andrews, and Robert Heath Jr. And the main objective of this article is to develop a conceptual framework from JCAS, so Joint Communication and Sensing Networks, using some information theoretic formulation of sensing and communication coverage and capacity. So first, a quick reminder of what is JCAS. So JCAS networks are networks which combine both communication functions with sensing services, like, for example, the localization of users or environmental sensing. There is also the detection, for example, or the target tracking. So it may, for example, allow us to enable precision navigation in some urban environment, to monitor activity in some area, or to provide collision avoidance services for autonomous vehicles. So the main challenge of JCAS is to deal with the intercell interference with tractable models that can be simulated numerically. And I'm going to try to show you how in this article they try to do this and to provide tractable models. So what are the main contributions and objectives of the article? So they try to construct a modeling framework from for JCAS network. And here are two fundamental questions they asked. First, what can be an appropriate conceptual framework for JCAS network? And secondly, how can the performance of communication and sensing together be characterized within this framework? So until there, in prior work, the stochastic geometry was very powerful for SINR analysis in wireless communications. So the idea of this article is to extend and to use these tools for radar tracking in JCAS networks. So here is the main outline of the article. So first, they give a model of JCAS networks and some mathematical modeling and assumptions on it. Then they will use an information theoretic approach for performance metrics, which is, I think, quite the very particular and original approach of the article. Then do some modeling assumptions to make the model tractable and to allow us to have analytical expressions, make approximations on them, and then obtain some numerical results. So I will go over these parts. So first, the model of the network and some assumptions of it. So here is the very basic scenario illustration for JCAS in cellular systems. So you have one cell, K, and several other cells behind. And so in one cell, you have a base station, so which will be abbreviated as BS, and several beams going to user equipments, and also some, I think, yes, so some sensing objects, which can be people, I don't know, buildings or blockage. So there are three main objects, I would say, in this kind of network, which has the base station, the user equipments, which we are trying to send the information, and the sensing objects, which are the blockage, or, for example, can be also people. So here is the mathematical interpretation of that. So we represent the spatial components of the network by the following tuple using point processes. So we use one point process for the base station, one point process for the user equipments, so the locations of the user equipments, and one point process for the location of the sensed objects. And for the blockage, we use a set process to represent the locations and the shapes of the blockages in the networks.
So just to be sure, so a set process is something that randomly draws some subsets of R2, or?
Yes, it's like a point process, but it's not using points. It's like, for example, rectangles or shapes.
Okay, not necessarily a partition, just
no, it's not
a bunch of shapes.
Yeah. Okay. So on these special attributes, we make some assumptions just for the model to be tractable later. So we take all the point processes to be stationary, mutually independent, and Poisson point processes. And we take the following assumptions on the intensities. For the blockage, we take it as a Boolean line process whose induced line of sight regions are approximated by the independent exponential blockage model. And the communication, this is quite an important hypothesis. We suppose that the communication may occur both in line of sight and non-line of sight links, but the sensing is only line of sight. It's, I think, just to make it easier for the computation tester.
And sorry, just for my curiosity, so what is Boolean in the Boolean line process? What does it mean?
It's like it just there is a blockage or there is not. Okay. I would say that it's if I remember well, there is 2 lines and the law of the height is like Boolean.
Okay.
Can I see it?
A picture? I think I don't have some.
I think it's simply it's a model that's by Robert Heath and one of and Tian by So you just sample a random variable which has which is distance based and independent for all angles. So there is no real geometry, right? And so in a Boolean geometry where you would have obstacles, you can check that the distance before obstruction is exponential.
Okay.
And you just do this independently per direction. So you sample 0, 1 random variable. That's it. Right?
Okay.
So as simple as that.
Okay.
That's what people use in the. So there are other models for obstruction, but I think that's what is meant here. Independent exponential blockage.
Okay. Thank you, François. So for the now, so we begin by modeling the communication capacity, which is like the well-known part, and then we will try to do the same for the sensing capacity. So for the communication capacity, we are using the Shannon formula, which is here and like gives the information rate in bit per second. So we take an AWGN channel and we denote the symbol rate as TS and have the following Shannon formula. So the idea is to get some inspiration from that and to define the sensing capacity. So this is what will be done next. So for the radar, the expression of capacity can be more difficult to characterize. So will be approximated using some information theoretic approach. So as you can see here, we will use the mutual information. So we do, as before, like some information over some time to obtain an information rate in bit per second. And so we have a vector of target parameters, theta, which is generally the range and the velocity. We use the mutual information, and TCPI is the processing interval. So I just put some note about the mutual information to explain a bit what it is and why it is used here. So if you take a pair of jointly continuous random variables, you will have the following expression for the mutual information. There is a much more general expression that I did not put here, but the main idea is that you try to measure the information that X and Y share. So it will measure how much knowing one of these variables tell you about the other one. So yes, quite telling example is that if X and Y are independent, the knowing of X or Y tells you nothing about the knowing nothing of the other one, so the mutual information is 0. So in our case, here is the mutual information that we are using. So the idea, as often in information theory, is to use the entropy to model the uncertainty. So you will model the information you're interested in as the mutual information between the parameter theta that you are trying to estimate and the return of this parameter, which is here and modeled by theta plus ns, which is like some kind of estimation noise, and can be seen, yes, as the total entropy. So you seeing the mutual information between the parameter you're estimating and the return of this parameter. So now, which setting are we using? So to characterize the estimation rate, we will use a setting which is a multi-carrier waveform. And here are some notations that we use. So there are NC subcarriers, and the maximum burst duration of the radar is NS multi-carrier symbol. So this is the symbol, and this is the multi-carrier, the subcarriers, sorry. And we take a subset of 0,1 to the NS times NC of these resource elements that we use for sensing. And we just note SINR and MN, sorry, the corresponding SINR on the resource element. So this is what we are going to use to make some approximation on the sensing capacity. So taking the expression we gave before, so yes, this one. So here we have a matrix R, which is just some covariance matrix for the estimation noise. So this is not very tractable. So we are trying to do some approximation. And for this approximation, we are using the Fisher information matrix. I will just explain after where does it come from. And so we obtain this upper bound for the communication, for the sensing capacity, sorry. And so this upper bound will be so named like that, and it will be the radar capacity that we are going to use for what follow. So having this, we multiply by TCPI, and can give 2 bounds. And now these bounds are in terms of SINR farad. I mean, to connect the information theoretic stuff with some stochastic geometry point of view. So this will be done using some constant G, which is just depending on the waveform parameters and the prior covariance for theta. So I'm just going to explain a bit how does this come. So just before I give a few notes about the Fisher information. So the idea of the Fisher information is to measure the amount of information that you have about a random variable. I mean that a random variable has about an unknown parameter theta. So you just take the density, you define the score as the derivative of the log likelihood, which is just the density but view in the point of view of theta. You can show that the expectation is equal to 0. And then you will just define the Fisher information as the expected value of the variance of the score. So it's like you want to see how big is the variance. So if it will give you like some, I mean, for example, Gaussian curve, and if the variance is very big or very small, it's a way to see, so yes, how much information has a random variable. So for example, if the curve is really flat, you won't have any information about the parameter because you won't really know where can you place the parameter. But if the curve is very thin, you will have much more information. So that's why you're using the variance of the score. So in our case, so how does this matrix appear? It's using the Cramer-Rao bound, which is a very well-known bound in information theory, and which tells you that the covariance on the estimate of the estimation node, which we call R, is greater or equal to J minus 1. And this equality, this matrix inequality means that just if you have A greater than B, it just means that A minus B is semi-definite positive. So the main idea of the demonstration here is just that, so you have the first formula here, this one, and you want to use the fact, so the Cramer-Rao bound to obtain this one, which is quite the same, it's just, yes, J instead of R minus 1. And the idea is just that if all your matrices are semi-definite and positive, I would say that everything goes well. So all the inequalities are going well. And so, yes, you can just verify it. And then, so for the second inequality, which is this one, and which is very important because it is the first place where the SINR really appears. The idea is that you just write the Fisher information matrix, which is quite easy to write because it's a 2 times 2 matrix because theta is a 2 times 1 vector. So it's a 2 times 2 matrix, and you just write it and using some inequalities. So yes, you use the following inequalities. So yes, by computing the matrix, so one just comes from the positive semi-definiteness of this matrix, and the other one just comes from the AMGM inequality. So using this inequality, you just define the constant J, so that this equality is true, and you obtain what I gave before. So the J constant is just here to, I would say, to make everything work. And since it's a constant depending only on the waveform and the prior covariance, it's quite interesting.
You went fast on what Q was.
Yes. So Q is, yes. So you have the prior, and Q is the covariance matrix for the prior. So then Q to the 1/2 is the square root, so it's the semi-positive, semi-definite positive matrix such that Q square root is equal to Q, and that prior is assumed Gaussian, so that's why you have the mean the prior and the covariance matrix Q.
What is the dimension means here? What is dimension of theta means here?
What the dimension of theta?
Yes, the number of measuring.
It was location and velocity. That's what
yes, it's the range and the velocity of the target you're trying to estimate. So the target has some range and some velocity, and you're trying to estimate both. So that's why theta is a 2 times 1 vector, and this gives you a Fisher information matrix of 2 times 2. So you can, yes, just compute it quite quickly and do all the inequality stuff just by extending the computations.
Just to be sure that I have well understood what is P. P is a prior, so it's a noisy version of the of theta, or I am wrong about that because I see it's a normal. It's normally distributed around theta bar, and I'm not sure if it's theta or what is theta bar actually.
Yes, theta bar is the mean of theta. The prior is the information we have before starting to estimate the parameter, the target parameter of theta. So at the beginning, we just estimate very roughly that it's equal to the mean, and that's why we are using that theta bar.
Okay, theta bar is the mean over what, over the time, or in the...
It is a prior.
It's a theta bar?
Yeah, if I get it correctly, this is a prior, right? So you have statistics on what you observe. You want to, this is radar, so you want to check whether it's a car or a pedestrian or things like that, and how it goes, at what speed, in what direction. Yeah, this would be the two-dimensional stuff.
Yeah.
So some type, perhaps yes, and
So in this model, you know. You know how to say that roughly what is the speed of the object that you are looking at. If you have a pedestrian, you know that you have a pedestrian or a car and that you are looking at that kind of object, isn't it?
no, you know statistics. The prior, if I get it correctly, is the so I mean you're in an environment where you already made statistics on velocity, type of objects that you want to detect, and things like that.
Yes.
This is prior.
Okay, I understand it's a prior, but let's say okay, you are in the street, you can have cars on pedestrian goes to 10 kilometers, I don't know, on cars goes to 30 kilometers, I don't know, something like that. And I don't see how a Gaussian law can model two different these two things at the same time. This is my question, actually.
I would say that I'm thinking.
So for speed, it's clear. For speed, you have an average velocity, and there is a variation of velocity around the speed, right?
Yes, but I think what the thing is that yes, we have already information about and this is that information that we are using for theta bar, and then we are trying to make it more precise with our estimations. But we are starting with some basis value and taking some mean over that basic statistics that we have.
Okay, no, it's okay, no problem. Thank you very much.
So I think it's Bayesian type statistics. So you have a prior, the fellow that you want to measure has its own parameter, but it's sampled from this initial distribution, and you use Bayes methodology to use the prior plus the noisy version of what you see in order to estimate by maximal likelihood or things like that because the n estimated is that you get so you send the signal.
Yeah, it's a return.
Comes back by reflection, and and all types of
take some noise and some noise, which is like the NS, and we take the sum of the two, which is like the return, and estimating the mutual information between the return that we are measuring and the target that we are trying to estimate. Okay.
Yes, okay.
So yes, so the main idea from there is that now we have a very interesting inequality. So this is called the sensing efficiency. We just multiply by this constant, and we have these two bounds, which will be very helpful because they depend on just some constant and the SINR for the sensing. Okay. So this is what motivates the following performance metrics. So one very important question raised by the article is how we can quantify the performance in that kind of network. And from what we saw before, the SINR in communication and sensing can be used to characterize in the communication case or to give bounds for communication and sensing capacities. So this is what leads us to define the following quantities. So for coverage, we consider the following probabilities, and for capacity, the following expected values. So it just comes from what we saw before. So yes, so from this inequality and from the equality about the communication capacity, we see that the SINR are good metrics to characterize the capacity. So that's why we are defining these quantities, which will be our metrics for performance in the network. So now it's time to make some assumptions about the model to make it more tractable. So and just to make it computable. So we start by giving the path loss functions. So for communication, as we told before, the communication can be line of sight or non-line of sight. So we define the two following path loss functions for both cases, which gives the path loss to the origin. And for the sensing, there is just a two-way path loss because, as we said before, the sensing is line of sight only. So we define the following two-way path loss. So as you can see, yes, the exponent here is minus, like minus alpha, and here it's the same, but for the exponential, it's like minus 2 gamma times r, and here it's minus gamma times r, which is quite important in the model. So now for the fading in the cross section, so if we consider the typical user equipments, we consider that it faces so rarely fading, so as written here. And for the typical sensed objects, it has cross section which is assumed constant and exponentially distributed, so like that. And now for the interfering links, the fading terms of these links are assumed IID and distributed using gamma laws. So just to explain quickly these gamma laws, to give an example, if you take both parameters equal to 1, you obtain the Rayleigh fading, so just marginal functions. To model here, yes, in one case, the fading term for the interfering links if you are in the line of sight or non-line of sight case. So we are keeping on with the assumptions. So now for the beamforming, we consider that the base stations and the user equipments are performing directional beamforming for both communication and sensing. And for a communication link, the base station and the user equipment select the beam direction, which maximizes the received power. Now, for the antenna, we just use, I would say, classical directional antennas with the antenna pattern following the sector model like Gmax and some constants like Gmax if you are not in this interval. Now, the association policy, which is quite important because it will have some consequence on the model after and the interpretation. So the typical user equipment will be associated with the base station that has the optimal path loss. So this is what is written mathematically here. And the typical sensed object is associated with the nearest line of sight base station. So this is what is written here. So now we can at least can finally give some models for the SINR. So for the communication SINR, it's like an already known model with here the term using the path loss function, and here just the sum and the sum over all the points of the so this is like the amplitude and some other constants which are like the gains of the antenna, and using also the path loss. And what we do from this formula is we try to define a similar SINR for the sensing case, so which I put here. And so it's a bit the same. So this indicator is like here to because you want to be only line of sight, and so you just taking some coefficients over time. Just a little thing, you see that here you have theta Tn, which is like similar to eta Mn, but you just reduced the dimension to time slots because I did not put it in here, but we have some assumptions which make it possible to reduce the problem not over the subcarriers, but over the time slots. So it's just a reduction over the time slots. Okay, so we have the following formula, and now we will try to make it tractable for the estimation of the probability coverage. So from there, the objective is to have some analytical expressions of what we did before. So for both SINR models, you see that the fading term is exponentially distributed. And then this allows us to characterize the distribution by the Laplace transform of the interference process. So here is just some general interference process. And if you have a general interference process like that, with phi being a Poisson point process, and just fading terms here and the path loss function here, you can use the Laplace transform of a Poisson point process formula sorry.
Okay. You're back in town.
Okay.
Nobody is going to continue the talk without you.
I think I need to share my screen
probably
again. Okay. Okay. So we'll try to remove that. Okay. So as I was saying, so we consider the following general interference process, and using the formula of the Laplace transform for Poisson point process, we obtain the following Laplace transform for the interference process. So this formula is very important because it's the one we are going to use, but it must be still approximated because the intensity measure here makes the computation of the integral quite difficult. So this is what the authors are doing next. Okay, so the idea is to use the Mellin transform of the path loss. So as I defined here, and the fact is that this Mellin transform will be more easy to compute. So using this transform, we define two functions. So I did not put their expression because it's very complex, but the idea is just that these functions are finite support approximation of the intensity measure lambda. So we use these constants to give two bounds to the Laplace transform. So it's like we just give finite approximation of this intensity, and using this finite approximation, we give two bounds to the expression here. So now we have a finite sum instead of this integral, which is a first good step. And after that, some Mellin transforms can still be a bit complicated to compute because, sorry, as you see, there is still some intensity measure here. So for the intensity functions that we are using, the associated path loss Mellin transform can be not tractable. So once again, we are giving some bounds. It's more the idea than the real expression that is important here. But yes, the idea is just that these bounds are expressed in piecewise poly-exponential functions, and these functions are possible to use to find closed form for the mailing transforms. So yes, quite a bunch of approximations and bounds, but yes, just to make it tractable. So okay, then we have we can use the following gamma, the generalized incomplete gamma function to find the expression and to have computable bounds for both the sensing and the communication coverage probability. So using this stuff, we can now get interested in maybe the most important part, which will be the numerical results. So first of all, here is a comparison of the coverage probability for sensing and for communication. And the general fact that we observe here is that the interference and blockage play the most important role in the link quality of sensing than for communication. So you have two things that you can see. Sorry. The first one is that globally the SINR is lower for the sensing than for the communication. So that's the first point. And the second point is that if you compare the SNR, so which is here and here, and the SINR, which is approximately here, there is a lot of different expressions which just correspond to all the bounds we computed. But yes, you can consider that it's approximately here. The gap here is about of yes 25 dB, and here it's less. It's about 15 dB. So you see that the interference has a greater impact for the sensing than for the communication.
The right curve is the SNR one, and
yes.
the SINR is a bunch of okay.
Yeah, so there is one SINR which is just simulated numerically, and some SINR that are computing with all the bounds. There are also some results that I did not specify here about how good and how sharp are the bounds. And in fact, one of the bounds which is used, which is SINR-GM, is very close to the real SINR. Okay, so the first result is that so the interference and blockage has a greater impact on sensing than on communication. So then we will get interested.
Can you explain that physically? What is the reason? Blockages, I understand, but interference. So
interference maybe. I would say that it comes from the fact that the sensing is in line of sight only, because you have, I would say, probably a bigger distance to go to find a base station, I would say. So more chance to get impacted by the interference. I don't know. That's just my.
I can compliment your. It's because the sensing is two-way. You send a signal to there, and you send
yes.
a signal back. But
yes. So yes, more distance because it's.
Okay, so you're more sensitive to anything else because it's twice.
Yes.
Twice. I mean,
yes, I think
not only
right.
twice, but also you reflect. It's only a very small part of the energy that comes back.
Yeah.
And therefore, I mean,
so much more impact.
The fact that many other base stations do the same.
Yeah, thank you. Okay, so next, another result. So about the ergodic efficiency. So here is some representation of the ergodic efficiency for a low blockage regime. So after that, I will show the same for a high blockage regime, but the general results are the same. So the interesting point that we are going to see is that if you take a more dense, a bigger density in terms of base station, it will. I'm sorry. Yes, it will have different impact on sensing and communication. So, as it is already known in the literature, for the communication, there is like an optimal point of cell radius. So here I would say around 75 meters. So here the SINR for communication is very good, But in the sensing case, it's quite different because as you may notice here, the more base stations there is, so the more dense is the network, the better is the SINR for sensing. So this means that like the needs, the exigencies for sensing and communications are quite different because yes, here you have a precise point, and here the more dense you get, the better is the SINR. Okay, so
can you remind us what the path loss function was for communication?
What is the path loss function
path
for?
loss function?
It's like r to the minus alpha and e to the times e to the minus gamma alpha and r. I think I will maybe put it again just to... Yes. These are the path loss for the communication. But yes, I mean, I did not really, I think, get the point on that because there is a last part in the article, which is, yes, comparing a bit the path loss functions that I did not put here because, yes, I had to make it shorter. But yes, I think there is a part in the article, a very final part, about yes, the comparison between the exponents, and so it can play a role.
What is the gamma here?
What is the gamma? It's like
It's a constant or random variable?
Oh no, it's constant.
Okay.
Okay.
And can you comment also on the your understanding of why this very big difference between the, so that's also perhaps Rodon's viewpoint, right? So actually, because I mean, it's very thin things that you want to estimate, so distance really matters a lot, and having smaller, having the thing to be sensed close is really way better, right?
Yes.
And before you're killed by interference or whatever.
Yeah.
So, okay, so this improvement of signal, I mean, having smaller cells means better signal, better reflecting signals, and not yet killed by interference. Right?
Ah, yes, yes.
Okay, that's
yes, because as you see in the beginning, the SNR is very high as compared to here, but it's hugely less compensated, so the general value is less. But yes, there is a first part where the interference plays a smallest role, and then another part where you will have a biggest degradation of the signal power because of just the fact that the just because of the scarcity of the base stations. Okay, so for a network with a high blockage regime, it's like the same interpretation. So as you see for the communication, there will be an optimal point, but for the sensing, the denser the network gets, and the better with the SINR be. So really the important point here is that there is a tension between the optimal regime for sensing and the optimal regime for communication, since as you saw, sensing is better for high density, high base station density, whereas communication is optimized, will have optimized performance for moderate to low base station density.
And when you mean regime, you mean the architecture of the network, so the density of
there are, yes, exactly. There are two densities here. There is the density of the blockage and the density of the base stations. So this represents the density of the base stations, and for the density of the blockage, I just put the two different slides. Okay, so I'm close to the end, so that's perfect. So to conclude, so a bit about what we did. So we used an information theory framework to extend the notion of coverage probability to the radar setting. So from communication to radar setting. And we defined it as the probability that the rate of information associated with a typical sensing target exceeds some threshold. We did some assumptions, focused on the multi-carrier setting, and gave some upper and lower bounds, which depend on SINR, so which was our way to connect from information theory to stochastic geometry. Then use that stochastic geometry framework, do some approximations, use some models to obtain tractable bounds, and then do computations, which led us to see, for example, that the densification of the network will improve sensing performance, whereas in contrast to the communication function, which will get worse. So just some ideas of future work that is possible. So for example, the use of different network sensing approaches or different parameters of interest. The study of the impact of the imperfect association between the sensed object and the serving base station. And for example, also the study of other forms of base station cooperation or sensing policies. And for example, the accounting of more structured deployments using not always, or just non-Poisson spatial models. Thank you very much for listening.
Are there any questions on the bridge or in the room?
Perhaps one question.
Go ahead, François.
So this Fisher information is only a bound, right? Okay, so can one go beyond that? We assume you are challenged and want to estimate this capacity, not in this. It's an upper bound on the Fisher information is
yes.
an upper bound. Right?
Yeah.
So when can you reach this upper bound? And if you're far from it, how can you better estimate what would be the grail of estimating this capacity in a non-Fisher regime or whatever?
Yes. So I don't remember well, but so yes, this all comes from the Kramer-Rao bounds. So I think yes, they can be reached. But to be honest, I don't remember in which case. But so if they are not reached in all cases, so I think yes, we can do better, but I don't know how. Maybe if someone has better knowledge of this can help, but I'm not sure about the exact condition in which the Kramer-Rao bound is reached.